The Netherlands is one of the strangest territories on the European map. From above, it appears as a land ordered with mathematical precision. Straight canals, perfectly divided fields, dense cities, colossal ports, and coastlines protected by structures that seem too large to belong to such a small country. But beneath this tranquil image lies a disturbing reality. A huge portion of the Dutch territory is at or below sea level, and millions of people live in areas that, without dikes, dunes, floodgates, and pumps, would be exposed to catastrophic flooding. Yet the country continues to function as if this threat were invisible. Trains, highways, modern neighborhoods, greenhouses, airports, and ports operate in a landscape that, in natural terms, should be extremely vulnerable. But how can the Netherlands live below sea level without flooding? The Netherlands is not simply a low-lying country. It's a delta. Its European territory lies where major rivers, such as the Rhine, the Meuse, and the Scheldt, meet the North Sea after traversing much of the continent. This means the country receives water from two fronts simultaneously. On one side, the sea pushes with tides, storms, and waves. On the other, the rivers bring enormous volumes of water from the interior of Europe. Add to this combination heavy rainfall, soft soils, subsidence, and a very high population density. The very name of the country reveals the key. Nederland means lowlands. The word is not a metaphor. Much of western and northern Holland consists of flat terrain, river sediments, ancient marshes, drained peat bogs, and reclaimed land. For centuries, the inhabitants didn't just occupy the available land. They shaped it. They drained lakes, surrounded floodplains with dikes, extracted water with mills and later with pumps, and transformed water surfaces into arable land. This process created polders, one of the essential features of the Dutch landscape. A polder is an area of land enclosed by dikes, where the water level is artificially controlled. It may be below the level of the sea, a river, or a nearby lake. To keep it dry, rainwater, seepage, or drainage must be removed through channels and pumps. It is land that exists because an entire system works to keep it dry. During the Middle Ages, many Dutch communities began to organize themselves around this need. Protecting low-lying land required cooperation. A poorly maintained dike didn't just affect one family, but everyone living behind it. This environmental pressure gave rise to very old water management institutions known as waterschappen, or water boards. Their role was to raise funds, coordinate works, maintain dikes, and decide how to manage canals and water levels. In a vulnerable territory, water management couldn't rely on occasional impulses. It needed continuity. The fight against water was also a fight against subsidence. In several regions, draining peat bogs and wetlands compacted and lowered the land. What at first seemed like a victory over water could create a new vulnerability. The more that was drained, the lower the surface level fell. And the lower the surface level fell, the more that land depended on dikes and pumps. The Netherlands didn't just build defenses against the sea. It built a way of inhabiting land that slowly changes beneath their feet. That is the central paradox. The country isn't dry because nature favors it. It's dry because it maintains a permanent infrastructure to counter natural processes that never stop. Water presses, seeps, rises, falls, erodes, carries sediment, and seeks new paths. The Dutch response is to anticipate these movements before they become a disaster. The classic image of the Netherlands is that of a seawall. While this image is incomplete, it remains essential. Seawalls are barriers of earth, sand, clay, stone, asphalt, or modern materials that separate inhabited areas from the water. Their basic function seems simple, to prevent water from passing through. But in reality, they are complex structures that must withstand hydraulic pressure, erosion, internal seepage, waves, soil settlement, and extreme storms. A seawall doesn't only fail when water breaches it. It can also fail from within. If water seeps through the seawall or beneath its foundations, it can carry soil particles and create internal channels. This phenomenon, known as piping, can weaken the structure to the point of failure. That's why Dutch seawall maintenance goes beyond simply checking the wall's height. It includes sensors, inspections, geotechnical analyses, reinforcements, and monitoring for even the smallest signs, such as leaks, deformations, or soft spots. Alongside artificial seawalls, coastal dunes play a crucial role. In several areas of the Dutch coast, dunes are a natural defense against the North Sea. They appear to be simple accumulations of sand, but they function as a flexible reserve of material. During a storm, waves can erode part of the dune. This loss does not always signify failure. The dune absorbs energy, deforms, and protects the interior. It can then be restored through natural processes or by artificial sand replenishment. Beach and dune replenishment is a fundamental technique. Instead of simply building rigid walls, the Netherlands deposits sand at strategic points so that currents, wind, and waves redistribute the material. This reinforces the coastline without turning the entire shoreline into a concrete barrier. The strategy recognizes that the sea is not a static adversary. A dynamic coastline needs to move, but within controlled limits. Polders complete this initial defensive logic. In them, water is managed as if the land were a large inverted bathtub. Everything that enters must be drained out. Previously, windmills were the driving force behind this system. Their image became associated with the Dutch landscape because for centuries they were hydraulic machines. They raised water from lower channels to higher ones until it could be discharged into rivers, lakes, or the sea. Over time, steam, diesel, and electric pumps replaced the windmills, but the function remained the same. A modern polder has drainage channels, pumping stations, sluice gates, defined water levels, and a management team that decides how much water to retain or release. The goal isn't always to leave the soil as dry as possible. In agriculture, nature, and urban areas, the water level must be balanced. If it drops too low, the soil can sink or degrade. If it rises too high, localized flooding occurs. Precision is constant. The modern history of water management in the Netherlands was marked by one night. Between January 31st and February 1st, 1953, a combination of a North Sea storm, high tide, and extreme atmospheric pressure drove water against the coasts of the Netherlands, Belgium, and the United Kingdom. In the Dutch region of Zeeland and other areas of the southwest, numerous levees gave way. Water surged in with devastating force. Entire villages were cut off. Houses, farms, and roads disappeared underwater. More than 1,800 people died in the Netherlands. The 1953 flood was not just a natural disaster, it was a technical and political revelation. It demonstrated that existing defenses were inadequate for a modern, densely populated, and economically strategic country. It also raised a troubling question. If a storm could breach so many walls in a single night, what would happen in the future with more urbanized coastlines, more expensive infrastructure, and an increasingly unpredictable sea? The response was the Delta Plan, one of the greatest hydraulic transformations of the 20th century. Its central idea was to reduce the vulnerability of the southwest Netherlands by closing or controlling several sea channels, estuaries, and inlets. Instead of defending every kilometre of inland coastline with long, exposed dikes, the country sought to shorten its defensive line. Less vulnerable coastline meant fewer weak points. From that program emerged the Delta Works, a series of dams, dikes, locks, storm surge barriers, and floodgates distributed primarily in Zeeland and South Holland. These structures transformed the landscape of the country. Some closed off sea inlets. Others allowed for the control of water flow. Together, they reduced the risk of flooding in a region historically exposed to the sea. The most emblematic project is the Oosterscheldekering, or Eastern Scheldt Barrier. Originally, completely closing the estuary was considered. However, that solution would have destroyed a large part of the tidal ecosystem and affected activities such as fishing and shellfish farming. The final decision was more complex, to build a movable barrier that could remain open under normal conditions and close in the event of dangerous storm surges. This solution maintained some of the natural movement of the tides while also providing protection. The Oosterscheldekering exemplifies an essential characteristic of the Dutch model. Engineering not only asks how to stop the water, but also what the consequences of stopping it will be. Closing off an inlet of the sea can protect a city, but it can also alter sediments, salinity, fauna, flora, and the local economy. The fight against flooding is never purely mechanical. Every project changes a living system. The Delta Plan transformed the Netherlands into a global laboratory for coastal defense. But it also imparted a less visible lesson. After 1953, the country understood that disaster is not fought only when it strikes. It is fought decades in advance, with scenario planning, regulations, budgets, institutions, and ongoing maintenance. Security ceased to be a reactive measure and became a matter of national policy. Among the most impressive structures in the Dutch system is the Maeslantkering, a movable barrier located near Hoek van Holland at the entrance to the Nieuwe Waterweg. Its function is to protect the Rotterdam area and part of South Holland from extreme storm surges from the North Sea. The importance of this structure becomes clear when considering what lies behind it. The port of Rotterdam, one of Europe's most important logistics hubs, as well as cities, industries, roads, and densely populated areas. The Maeslantkering is not a fixed wall. It consists of two enormous curved gates, each connected to gigantic metal arms. Under normal conditions, the gates remain open on lateral dry docks, allowing ships to pass to and from the port. When a dangerous combination of tide and storm is forecast, the system can close the waterway. The gates float to the center of the channel, partially fill with water, and then lower until they rest on the bottom. At that moment, the sea encounters a closed door. The sheer size of the structure is almost unimaginable. This isn't your average industrial gate, but a machine the size of a monument. Its design had to solve a seemingly contradictory problem, protecting a vulnerable region without permanently blocking one of the continent's most important maritime corridors. A fixed dam would have been simpler, but it would have disrupted port activity. The solution was a defense that only appears when needed. This principle is repeated in various parts of the Netherlands. Mobile barriers allow people to live with the water in normal times and isolate themselves from it during extreme events. It's an engineering of intermittent presence. The country doesn't live behind a closed wall all the time. It lives behind a system capable of changing configurations. The operation of these barriers requires trust in meteorological models, sensors, communications, protocols, and automation. The danger lies not only in the force of the water, but in the precise moment of action. Closing too late can be fatal. Closing too early can disrupt navigation, the economy, and water flows. That's why controlling a barrier isn't a simple visual decision. It depends on predictions of sea level, wind, atmospheric pressure, river flow, and safety margins. Dutch engineering here resembles a form of anticipation. The system doesn't wait for the water to hit the city. It calculates its arrival before it happens. And that calculation must be precise enough to justify the movement of gigantic machines. There's something almost mysterious about this normality. Millions of people sleep, work, and travel in areas that depend on monumental gates, often invisible to daily life. The country functions because these structures are ready to act during a few critical hours that can define the fate of entire regions. While large barriers attract attention, the Netherlands' daily survival depends on a less spectacular infrastructure, drainage. A low-lying country isn't only flooded by the sea, it can also be flooded by rain, seepage, groundwater, and saturated rivers. In many polders, water has no natural outlet because the land is lower than the surrounding canal, river, or sea. To remove it, it must be raised. Pumping stations are the heart of this operation. Some are small and local. Others are enormous facilities capable of moving massive volumes of water. Their job is to maintain defined levels within networks of canals. When it rains, water falls on roofs, streets, fields, and roads. Some seeps into the ground. Some runs into ditches and canals. From there, the system directs it to stations that pump it to higher bodies of water. This network functions as an artificial circulation system. The canals are not just landscape features or tourist routes. They are hydraulic arteries. They allow for the storage, distribution, and evacuation of water. In cities like Amsterdam, Rotterdam, Utrecht, and Leiden, the canals are part of the urban identity, but also of a long history of water management. Behind their tranquil appearance lies a logic of levels, sluice gates, drainage, and regulation. The complexity increases because not all the water needs to flow out immediately. In dry periods, the Netherlands also needs to conserve fresh water. The same country that fears flooding can suffer droughts, salinization, and water shortages for agriculture, nature, and industry. If too much fresh water is discharged into the sea, there may be a shortage in the summer. If too much salt water enters through rivers or canals, crops, ecosystems, and supplies are affected. Water management is a choreography between excess and deficit. Climate change complicates this choreography. Intense rainfall can overwhelm urban systems in a short time. Dry summers can lower river levels and increase saltwater intrusion. Rising sea levels increase the pressure on floodgates and defenses. Land subsidence exacerbates the difference between inhabited land and the water above. The challenge is no longer just about building higher. It's about managing more variable systems. Technology helps, but it doesn't replace maintenance. A clogged canal, a malfunctioning pump, a poorly coordinated gate, or a weakened dike can create local problems. That's why Dutch security relies on routines: measurement, inspection, cleaning, repair, standard updates, and scenario simulation. Water infrastructure is never finished. Each generation inherits previous works and must adapt them to new threats. This is one of the less visible keys to Dutch success. Many countries build large structures after a catastrophe. The Netherlands has built a culture of daily management. Water isn't controlled solely with concrete and steel monuments. It's controlled with annual budgets, specialized technicians, water boards, sensors, maps, protocols, and a national obsession with down to the last centimeter. For centuries, the intuitive response to water was to build higher dikes and keep it out. This logic saved territories, but it also had its limits. When a river is confined between high dikes, the water doesn't disappear. It simply flows higher and with greater pressure. If an extreme flood occurs, the failure can be devastating. Furthermore, by preventing the river from using its natural floodplains, the space available to absorb exceptional flows is reduced. In the late 20th century, the Netherlands faced a series of alarming river floods. The threat came not from the sea, but from the rivers. The most innovative response was the Room for the River program. Its principle changed the question. Instead of asking only how to contain the water, it began to ask where to allow it to expand safely. The program included measures such as moving dikes inland, lowering floodplains, creating secondary channels, deepening riverbeds, removing obstacles, and reserving areas where water could occupy space without destroying cities. This strategy is not about surrendering to the river. It is about directing its expansion toward prepared areas. During a flood, water needs volume. If the entire area is enclosed, urbanized, and protected by walls, the river level rises. If there are areas of controlled expansion, the flood loses height and energy. In practical terms, giving the river space can be more effective than confining it. Room for the river also transformed the way we think about the landscape. Hydraulic works ceased to be seen merely as grey defences and were integrated with parks, nature reserves, adapted agricultural areas, and new public spaces. Flood protection was combined with urban quality and environmental restoration. Instead of erecting a rigid boundary between nature and city, territories were designed to be able to flood without becoming a tragedy. This approach reveals significant technical maturity. The Netherlands understood that not all water needs to be expelled. Sometimes, security lies in deciding where it can enter. That decision requires risk maps, agreements with communities, compensation, territorial redesign, and a long-term vision. It is not a simple solution because it implies accepting that some areas will have a hydraulic function during extreme events. In a country where every square meter has value, reserving space for water is a profound decision. It means that the territory is not organized solely for immediate economic reasons, but for collective survival. The apparent mystery of the Netherlands, living below sea level without flooding, is not solved solely with giant barriers. It is also solved with humility in the face of rivers. The country learned that water can be an enemy when ignored, but also an ally when guided. Room for the river represents that paradigm shift. It's not about conquering water everywhere. It's about carefully choosing the places where it can move. National flood defenses are insufficient if cities are not prepared for extreme rainfall. In a more variable climate, an intense storm can overwhelm urban drainage systems, even when the sea is calm and rivers are not running high. That's why the Netherlands is also working on urban adaptation. The question is no longer just how to protect the country from its borders, but how to make each neighborhood more water tolerant. Rotterdam is one of the best-known examples. The city combines a port, industry, densely populated neighborhoods, and low-lying areas. There, water plazas, green roofs, floodable public spaces, and temporary storage systems have been developed. A water plaza can function as a sports field or recreational space on normal days and as a reservoir during heavy rains. Instead of sending all the water immediately into the sewer system, it retains it and reduces pressure on the system. Green roofs serve another purpose. They absorb some of the rainwater, slow runoff, improve thermal insulation, and reduce the urban heat island effect. In a low-lying city, every minute of delay can matter. If all the rainwater reaches the drainage system at once, the gutters and pipes become saturated. If some of it is retained on roofs, in gardens, parks, and reservoirs, the peak pressure decreases. There are also neighborhoods and homes designed to coexist with fluctuating water levels. Some floating or amphibious houses can rise with the water level in controlled situations. They are not a solution for the entire country, but they illustrate a central idea. Adaptation is not always about keeping water away. Sometimes it's about designing buildings capable of tolerating its presence. In port and riverside areas, urban planning incorporates safety margins, evacuation routes, raised ground levels, local barriers, and resilient materials. The city is conceived as an extended hydraulic infrastructure. Streets, parks, parking lots, plazas, and buildings can all be part of the system. This urban adaptation is less visible than a storm surge barrier, but it is becoming increasingly important. Modern floods don't always arrive like a cinematic wave from the sea. They can appear as rain that overwhelms drains, a slowly rising canal, a combination of high tide and blocked drainage, or seepage that affects basements and tunnels. The threat is multifaceted, and therefore the response must also be multifaceted. The urban subsoil adds another layer of complexity. The Netherlands has tunnels, underground parking garages, electrical grids, a subway, sewage systems, and cables in areas where groundwater must be controlled. A low-lying city doesn't just protect its streets, it protects what lies beneath them. This subterranean dimension creates a silent vulnerability because many flaws go unseen until water has already entered. The modern Dutch city resembles an organism designed to absorb shocks. It is not invulnerable, but it has redundancies. If one part receives too much water, another can store it. If a canal rises, a floodgate regulates the flow. If rainfall exceeds a certain threshold, a public space changes function. Urban normality is sustained by this capacity for rapid transformation. The Dutch system is one of the most advanced in the world, but it doesn't eliminate uncertainties. Climate change poses an uncomfortable question. To what extent can a low-lying country adapt if sea levels rise for centuries? Scenarios vary depending on global emissions, the dynamics of polar ice, and the response of the oceans. But the general direction is clear. The sea is rising, and a deltaic country must prepare before the change becomes irreversible. The difficulty lies not only in average sea level. Storms, tides, waves, river discharge, and land subsidence also matter. A rise of a few centimeters may seem small, but in low-lying coastal systems it alters safety margins. A sluice gate must close more frequently. A dune needs more sand. A dike requires reinforcement. River discharge into the sea can become more difficult if the sea is higher than the river during certain periods. Land subsidence exacerbates the challenge. In areas with turbidity or soft sediments, the land can continue to subside due to compaction, drainage, and human activity. This creates a kind of scissor effect. The sea level rises and some of the land subsides. The relative difference increases. Engineering must respond to both movements. The Dutch Delta program addresses these problems with long-term plans. Its approach includes flood safety, freshwater availability, and spatial adaptation. Protection is no longer just for the next storm, but for decades. The country works with scenarios, regular reviews, and phased decisions. Instead of choosing a single, definitive solution, it seeks to keep options open. This flexibility is crucial because no one knows with absolute precision the future pace of change. If sea levels rise moderately, reinforcements, more sand, better barriers, and territorial adaptation will suffice. If the rise accelerates due to massive ice loss in Greenland or Antarctica, the decisions could become much more radical. On that horizon, enormous questions arise. How much can the coastline rise? Which areas should always be protected? Which infrastructure should be adapted first? How to ensure fresh water, and what to do with territories that are becoming increasingly expensive to maintain. The unsolved mystery isn't whether the Netherlands knows how to defend itself today. The evidence shows it knows how to do so with extraordinary effectiveness. The mystery is how long this balance can be maintained if the planet's conditions change faster than human endeavors. The answer doesn't depend solely on Dutch engineers. It also depends on global emissions, international politics, the economy, technology, and the behavior of ice sheets located thousands of kilometers away. Even so, Dutch history reveals an advantage. The country doesn't wait for the problem to become visible before acting. Its hydraulic culture is based on anticipation. This doesn't guarantee absolute security, but it reduces improvisation. In a world where many coastal cities react late, the Netherlands studies scenarios before they become emergencies. The great lesson is that living below sea level doesn't mean arrogantly defying nature. It means accepting its rules with extreme precision. Every dike, every pump, every canal, every barrier, and every flood zone is part of a fragile pact. The water always seeks to return. The Netherlands always calculates how to prevent it, divert it, or receive it without collapsing. In short, the Netherlands lives below sea level because it transformed a geographical threat into a national structure. Its security doesn't depend on a single project, an isolated invention, or a rigid border against the ocean. It depends on a comprehensive system comprised of dikes, dunes, polders, pumping stations, canals, movable barriers, urban plans, waterboards, climate models, and political decisions sustained over centuries. The key lies in continuity. An abandoned dike ceases to be a defense. An unmaintained pump becomes a vulnerability. A city that waterproofs its entire surface accumulates risk. A coastline that doesn't replenish sand loses protection. That's why the Dutch model functions as a permanent surveillance system. The country didn't defeat the water all at once. It manages it every day. It also learned to adapt its strategy. First, it built defenses to keep the water out. Then, it constructed monumental structures to close dangerous inlets from the sea. Later, it understood that some rivers need space, that some squares can store rainwater, and that some cities must be designed to coexist with extreme events. This evolution shows that protection is not a fixed idea. It is a continuous adaptation. The paradox remains. One of Europe's most orderly, prosperous, and densely connected countries sits on land that, without human intervention, would be far more vulnerable. Beneath its roads, ports, farms, and modern neighborhoods lies a silent machine that sustains daily life. Water is always nearby, sometimes above, sometimes behind a barrier, sometimes underground, sometimes waiting for a storm. The Netherlands doesn't flood because it has learned to read water like few other places in the world. It measures it before it arrives, contains it when it threatens, pumps it out when it accumulates, and gives it space when necessary. This combination of calculation, historical awareness, and engineering transforms a low-lying country into a hydroelectric powerhouse. But the tension remains. In the future, the sea will rise, rivers will change, and storms will test every safety margin. Dutch history is not yet over. It continues to be written in centimeters, floodgates, and tides.